Alright, hello everyone, July the 7th. Let's do this. Put marbles in the bag. Put marbles in the bag. I've done this before. Okay. You have K bags. You're given a zero index integer array weights, where weights I is the weight of the ith marble. You're also given the integer K. Divide the marbles into K bags according to the following rules. No bag is empty. If the ith marble and the jth marble are in the bag, then all marbles with an index between them should also be in that same bag. If a bag consists of all the marbles with an index from I to j inclusively, then the cost of the bag is a weights I plus weights j. The score after distributing the marbles is the sum of the costs of all the K bags. Return the difference between the maximum and minimum scores among marble distributions. Okay, so what do you think? K bags, and then we want to distribute it into, no, we want to distribute into K bags, and the rule of distribution is we have to basically we divide this array into K subarrays, or you can even think of we just putting dividers in among the weights, and when this is K equal to 2, so we basically say one divider, right? We put a one divider because it says if ith and jth are in the bag, then all the marbles, right? So if we have 2 in the bag and everybody in between is in the bag, so yeah, so you just put in dividers. Doesn't matter how much K is, right? You just put a divider, K minus 1 dividers in them, okay? So once you put that, then what you need to know is the sum, right? The sum, the cost of each bag, the marbles with an index I and j. So the start and the end, okay? The start and the end. And the score. So the score is add them together. Add them together, okay? And we want the maximum and the minimum score among the distribution. Okay. We have 1, 3, 5, 1. And K is equal to 2, which means we have only one divider. So we throw a divider, and then we have, the smallest and the biggest to divide. Yeah, let's say we divide here. We have, this is 1 plus 1. This is 3 plus 1, right? If we divide here, that's going to be 1 plus 3, 5 plus 1, 1 plus 5, and 1 plus 1. So that's all the possibilities. And this is 2 plus 4. This is 4 plus 6. This is 6 plus 2. So this is the max, and this is the min, and the difference between the two. Okay. And we can divide into many different. Difference between a max. So we need to find the max and we need to find the minimum. can we find the maximum score? What if the question is just find the maximum score, right? Okay, so we want to find a maximum score, which means a certain way of divide we can get the result is the maximum. But how would you want to do that? Maybe we can do, I don't know, is DP gonna work on this one? How many bags left? And the current position? No, that's gonna be O1K. That's definitely too big. Yeah, there gotta be a smarter way to do this. The maximum score and the minimum score. And the difference between the two. Yeah, let's say we have a minimum score, okay. And then we have a maximum score, okay. And the difference between the two. Interesting. I have no clue at the moment. What's the observation here? Yeah, let's get a bit more. Let's have 6. Let's say k equal to 3. So yeah, so we have to do, 2. And basically, one end is gonna be A0 plus one of these. Okay? And the next one. So if we find a maximum, if we want everybody to be the max, I mean, it cannot all be max. We can say, I don't know, put in here. And then you find the maximum for the remaining. But then you can do this, right? Huh. Well, if k is equal to 1, then yeah, it's triple. If k equal to 2, now you have to go through the whole thing to find it. If k equal to 3, how do you handle if k equal to 3? You're gonna have to we can do k equal to 1 and then you split. Hold on. Once you find the largest, okay, and you split it even further, do you make it bigger? What do you think? I mean, the more you split, right, you're basically adding more to the result, okay? So if we say k equal to 2, and we know this value and this value, they must be included. If k equal to 2, we basically, okay, we want to find a pair that has the largest sum, right? Yeah. If let's not do k equal to 3. Let's try k equal to 2 at the moment, right? If we do k equal to 2, we need to draw, right, a separation somewhere. And because the end values are certain, they don't change. So what we're actually looking for is the maximum pair. Ooh, maximum pair. Can we do something about that? Maximum pair, right? If k equal to 2, you want to find the maximum pair, then you get it. What if k equal to 3? Well, if k equal to 3, I want to find the maximum pair and the second maximum pair, right? Because we do 2, right? And the score is this plus this, this plus this, this plus, and then this plus this, right? It's the same as this plus sum of this, and this. Oh, I think I see what this one's asking for. We want to find the maximum. So when we do the max, we want to find the maximum pairs, consecutive pairs. Okay. Now, what if the maximum have overlap? What if like this is the maximum and this is the second maximum? What if we have this situation? What you gonna do? I guess we cannot do it that way, can we? Yeah, because each one can only be used once, so you really cannot do it that way. Nah, you cannot. You cannot do it that way. Which means if we have a situation like this, we pick the max. Ooh, that's actually okay. If the max pair do not overlap, perfect. We're done, right? If the max pair do not overlap, what if they do overlap, right? What if they do overlap? Yeah, we'll say we have A1, A2, that's big, and A2, A3, that's the second biggest, okay? And I call A4, A5 as the third biggest. So in this case, of course, if we want to do the max, we pick the max, and we pick this. So this doesn't matter. No, it does not matter because they can only be used once. It cannot use twice. So yeah, we go the largest, we record which one is used, and the next one cannot be repeats, right? If it's used, then we don't use it. Because if we use this, then we cannot use this. What if they are the same? Oh God. What if they're the same? Yeah, what if this and this is the same? Okay. So these are the same, and A1, A4 is the third one. Yeah. How about we have this situation? What if this is equal to A2, A1, A3? Okay. They're the same. And A1, A4 is the third biggest. Now if we pick A2, A3, now this is A2. This is 3, A3, A4, my bad. If we pick, right, A2, A3, then we cannot do A3, A4, right? And we actually can make it smaller. But if we pick A1, A2, then we can do this. So I guess the idea, yeah, what are we gonna do? I mean, we're gonna do, let's take a dictionary, right? We have the pair sums, right? We have the pair sums. We have a value, and we have a list of pairs. Okay, so I have v0, v1, v2. They have a list of values. All right. And we sort them. Okay, so we look at the biggest one. And we try to pick one of them. Okay. Then we go to the next one. We try to see if we can pick. And we go to how long that's gonna take. I don't know how long that's gonna take. Come on, how long? I'm not sure. That might take a while. Is that the solution though? Can we make these choices? I mean, if it's only a single choice, yeah, I can see, like, if you choose this, if everything is, you know, connected, if you choose this, then you have to give up the second largest. Then you pick, you know, the third largest. Or, yeah, that's actually fine, right? No, I mean, if we have lots of k, well, we have lots of k, and how do you make the decision which one to pick? Like, seriously, how do you make the decision? Okay, we have the biggest, but picking the biggest might not be the best choice, right? It might not be the best choice. Can we make this one faster? I feel like we find the first breakthrough, but then there's the second one we kind of get stuck again. Yes, we know we need to find pairs, but if you find the sum of pairs, we're going to have the same length, right? We have the same length, 10 to the 5th. We have 10 to the 5th pair sums. We can sort them, which is fine. It's okay, we can sort them. But then, how are we going to make the choice which one to go for, right? To get k, we need to get k, okay? We need to get k. And we can pick the largest. And then what? And what if, hold on, what if I want to do like, I mean, if I do this, then yes, this plus this. What if I do this again? Oh, look at that. Oh, hold a second. We don't have a problem. All right. So, these two have to be picked. So if I do this, right? Okay, A1 plus A2. If I do this, that's A2 plus A3. Oh, it's no problem. No problem at all. Yeah, if we say k equal to 3, right? And then we break this into 3, then our cost is A0 plus A1. Right? And then A2 plus A2, and then A3 plus A5, which can be translated into A0 plus A1 plus A2, A2 plus A3 plus A5, right? These two are equivalent. 0, 1, 2, another 2. Oh, so it's fine. Oh, then we solved this problem. Then we solved it. Yeah, then we solved it. Yes. So we don't have to worry about picking them because you can do this way. Yeah, you can. If A1, A2 is the same as A2, A3, so we have a what's it called? Repeat, right? Overlap, and then they both are largest. We can pick them both because we just single out A2, so A2 can be counted twice. Okay, so now we got it. Now we got it. We can solve this problem. observation. Another observation. I'm not sure. I think I probably solved this last time by myself as well. Not 100% sure, but it doesn't matter. So what we need to do is I need to, so I just get the consecutive, right? Okay, I get the consecutive, and yes, you just get the consecutive, that's it. Pair sums. Okay, for I in range, len weights -1 because it's consecutive, len -1. We do weights I plus weights I plus 1. Okay, so these are the consecutives. And we will do that, and we will sort them. Right? Okay. So we do that, we'll sort them. And based on k, we're going to take k minus 1. Okay? So pair sum k minus 1. These are the smallest, right? So we find the smallest and pair sums. We also need the largest, k minus 1. So we say k minus minus k minus 1. Okay, so I think we'll return this. I think this might be right. Okay, let's run some for 0. This is weights. Okay. Put marbles, weights, and k. That ain't right. Oh, we have to sum them. Dude. Sorry. Yep, I think that is it. I mean, you can, if you're not certain, you can do this, and we can always do this. Some test cases. Yeah, I'm pretty sure that is the one. No way. Got it wrong. Okay, too excited. Oh yeah, k equal to 1. K equal to 1. We have 0. We don't put anything. I think k equal to 1 should be a different case. Should be a special case, because if we should get k equal to 1, this is from 0 to the end, and this is not right. Because this is trying to find the smallest, but we don't get any pairs. So I think if k is equal to 1, I'll return 0. Okay, I think I need to put this one here. Yep, we got it. So I'm pretty sure I got the last time as well. I think even the error may be the same. Yep. was the previous I call run on exactly the same thing. This one passes. Oh, you use this. Oh well. That's okay. N largest, N smallest. I do not remember that. Oh, pairwise. I do not. Pairwise and. Dude, N largest and N smallest. Equals solution. It does look like magic. I don't remember at all. There's pairwise. Okay, we'll probably do that one, but let's. No, what we want to do is this thing. Let's put it up. 2551. So the idea, right, is that to break apart weights into k-bags, we need to insert k-1 separations into the array, right? And each time a separation is inserted, the score increases by the sum of the consecutive pair of weights on either side of the separation. This means to find the max score, we need to find the max sum of consecutive pairs. All right. Similarly, to find the smallest, the min score, we need to find the min sum of consecutive pairs. The pairs can share element, because in the case of A0, A1, A2, if we put separation between A0 and A1 as well as A1 and A2, the score will have A1 duplicated. A0 plus A1 plus A1 plus A2, right? We'll have it duplicated. Thus, we don't have to worry about a value, right, being shared by two consecutive sums. Oh, and login. Okay, so that's solution 1. Solution 2. Some application of built-in method. We can say pair sums equal to sorted W1 plus W2 for W1, W2 in import iter_tools. iter_tools.pairwise weights. Actually, we need to go to iter_tools. Oh. Documentation. iter_tools. pairwise. Return successive overlapping pairs. Oh yeah, that's exactly what we want. So we do that and import heap queue. Right, return sum heap queue dot n largest. Right, dot n largest pair sums. Right, how many? K minus 1 minus n smallest. Yeah, this is fun. Int is not iterable. Where did we go wrong? Oh, n first. Dude. K minus 1 first. Sorry. There we go. Good. And we don't have to worry about equal to 1. Very interesting. Just for fun. Okay. So that's that. All right, we can continue. We spent half an hour on this one. Yep. I'm gonna log in. Does this count as greedy? It does. It does count as greedy. All right, let's have some fun. Determine the winner of a bowling game. You're given two zero-indexed integers, okay, that represent the number of pins that player 1 and 2 hit in a bowling game. The bowling game consists of n turns, and the number of pins in each turn is exactly 10. Assume a player hit xi pins in the ith turn. The value of the ith turn for the player is 2 times x if it hits 10. Otherwise, xi. Score the players is a sum. Return 1. Oh, he just add them together. Wait. 2 times x if the player hit 10 pins in any of the previous 2 turns. Oh, so we have to check back 2 times. So this, yes. This, yes. So it has, oh, okay. Okay, 2 turns, right? Yeah, we just check back 2 times, right? Or you can, record, like we have a 10 and we have the turn. We set a turn, right? Good for, right? Good for 2. So now we go here. It's good for, good for 2, good for 1, good for, actually no. So this, when we go to the next one, the good for need to minus equal 1, right? It's a minus equal 1, unless if it's, yes. Okay, so I think I know what we're gonna do on this one. So this is 60. So basically, oh, zip. Nah, not zip. We just do both. Yeah, we have to do both. So okay. So S1 equal to 0. Okay, for P in player 1. Good for. Okay. If good for minus equal 1. All right. And then we shall say if good for s1 plus equal to p times 2, right? And if p is equal to 10, good for equals 2. Okay. So we're gonna do this for this, and then we're gonna do this. Let's, you know what? Def compute score pins. Okay. And we'll return int. S equal to this. S, this should be pins. Right, and then we'll return if good for, else s plus equal to p. Maybe we can do this. S plus equal to p times 2 if good for, else 1, save some. Return s. Then we'll say if score s1, s2 equal to compute score players 1, compute score players 2, and if s1 is larger than s2, return 1. If s1 is smaller than s2, we'll return 2. Otherwise, return 0. All right, let's give this a shot. Let's see this good for idea if it works. Let's use all of them. Looks good. Let's give it a shot. Oh my god. You gotta be kidding me, man. You're killing me this one. It's a simple question, man. Output 2, expected 1. Okay, so dear God. So first one, if good for no. So good for 2, yeah, and the next one. Huh. It is wrong. Dude, come on. What the hell? So it should be putting here. Yeah, I think I misunderstood some stuff. That's fine. That's fine. Oh, that will be so... I'll be pissed off in the actual competition. Yeah, I'll be pissed off. It's such an easy one to deal with, and then you just added 5 minutes to your result. Jeez. All right, so this one's done. First, completely painted row or column. You are given a 0-indexed integer array and an n by n matrix. Okay, so permutation of integers from 1 to m times n. Go through each index I in array starting from 0 and paint the cell in matrix containing the integer. Okay, return the smallest index I at which either a row or a column will be completely painted. Interesting question. Interesting question. Let's see. So for this, we start from Wait, hold a second. What the hell is this? Paint the cell in matrix containing the integer. Oh, we have to translate first. Which is fine. I'll translate. That's okay. So I'll translate. So we know which one gets painted. So we paint 1. Then we paint 3. Then we paint 4. 4. So that's the index. Smallest index. Okay, so basically we need to have a fast way to check if a row or a column has been painted. Now, how do we check? Well, we can use a I was gonna say priority queue, but oh yeah, we don't need priority queue. I just need to know the number, right? So every time we paint, the row will increment, the column will increment by 1. So we need to find the first time that it reaches. Yeah, I think that's not really that hard. So we can give this a shot. Give this a shot. So this is how I would propose. We need to have rows and columns. But first of all, I need m and n. So because I don't know what they are, so I'm gonna do mat 0. Okay. So we get m and n, and then I need to know which one is which. Dude. So we need to know the positions. It's gonna be, oh god, for I in range m, for j in range n, right? It's gonna be dictionary of mat ij. Okay, it can equal to I and j. So something like that, right? So I have positions, and I have row counts. 0 times row m, right? And then we also have column counts. We count the number of cell that has been filled. So now we can say for I, now let's say for k in range, for ka in enumerate. How about that? In enumerate array, we say ij will equal to positions a, right? And then we painted it, so we say row counts, the ith row, well, plus equal 1. Column counts j plus equal 1. If row counts I is equal to row counts m, or column counts j. No. Row counts is equal to n. On the row, we count how many values in the row have been painted, so it's n. This is m, right? When this happens, we'll return k. Otherwise, we will return k no matter what, so you don't have to worry. Okay, let's just pull this up. Put this one here and run it. Does it work? I think so. I think it works. Didn't run any test cases. Yeah, it does work. Count the number of cells painted on each row and column as we go through array. First time either a row or column reaches the number of reaches n or m, we have we will have found the answer. So we call it OMN because this is OMN and this is OMN and most, so that's that. Okay, so this one is done. I'm pretty sure the solutions are pretty much the same using map. Yeah. Okay, so that's that. All right, minimum cost of a path with special roads. You're given an array start, where the start has an index, represents your initial position in a 2D space. You are also given the array target, where target represents your targeted positions. Okay, the cost of going from a position to any other position in the space is, I think that's the Manhattan distance. There are also some special roads. You're given a 2D array special roads, where special roads I equals this indicate that the ith special road can take you from this position to this position with a cost equal to this. You can use each special road any number of times. Return the minimum cost required to go from Dijkstra. We will Dijkstra this stuff. So, I mean, basically, wait, can we read Dijkstra? So we have the positions, right? This one we have, we start from 1, 1, we need to go to 4, 5. 1, 2, 3, 4. 2, 3, 4, 5. Okay. And every single position is a member, right? So, and this is from 1, 2, 3, 4. 1, 2, 3, 4, 5. So we say from 1, 2. So 1, 2 to 3, 3 here. 3, 3 is about here. So we have a path will cost you 2. Otherwise, it's gonna cost you 3 minus 1 is 2. 3 minus 2 is 1. So it's gonna cost you 3. So this is a shorter path. Or you can do from 3, 4. 3, 4 to 4, 5. 4, 5. Oh, this one. With a cost of 1. So you say it'll be 1, 2, 3, 4, 5, right? Huh. Interesting. Yeah, like this. This is actually worse, right? Oh, this is worse as well because this should only take 2 and this one take 4. This is also worse. This is also worse. So you might as well just go directly there. Now, the one thing is, if you go through any, so this is the start, right? This is the start, and this is the end. So if you go through anything in between, it's the same as going from this and this because it's Manhattan distance, right? It's Manhattan distance because anything that's inside this grid, if you go outside, yeah, it's going to be longer. So why would you do that? So you go directly. So in this case, it'd be 3 plus 4 would be 7. No matter where you go, however many you pick inside, as long as you follow the same directions. Let's say you always go right and up or right and down. You follow the same to go there, and then the cost is the same. If you do, you turn back, you go in circles, and of course it's going to cost you more. But if you just go directly, so the baseline is always do a direct, okay? And then the question is, if there are paths that that can make it faster. Yeah, exactly, right? So we are going 1, 1 to 1, 2 to 3, 3, right? To 3, 4 and to 4, 5. As we go directly, just going this. So this is 1, right? This is 3, so we have 4, we have 5, and 6, 7. Yeah, it's 7, cost 7, which is exactly the same as doing this. But if we incorporate, so yeah, this is interesting. So now we need to figure out how we're going to incorporate this. Which, what I think, if we Dijkstra this, right? If we Dijkstra this, we consider these are nodes, right? These are nodes. And between the nodes, we have between the nodes, I mean, we go through all the special roads. If the special roads are worse or equal to not using it, then yeah, there's no way we use it. So we pick out the ones that are good, right? Or pick out the ones that are good, which means they have smaller cost. Okay. All right. So now we have a bunch of rows that have smaller cost, but they can be all over the place, right? They can be all over the place. Now the question is, which one to use? Yeah, that's the question, which one to use. That's what I think. I think we need to do Dijkstra. But if we do Dijkstra, special road is 200 in length. Okay, special road is 200 in length. So most we have 200 things to consider. Okay, let's say we have 200. And when we have 200, we have, 200 times, 200 times 2. We have 400 nodes, right? Plus the start and plus the end. And each time when you start from something, you will go through 400 of them. Go through all of them. Okay? And then you will record the current. And so you put all these nodes inside. So basically have a graph of size 402, right? A graph of size 402. And everybody is connected to everybody else. Jeez, man. So you start from 1 and you put everybody else into the priority queue. Okay? And the next one, somebody pop up, the smallest, right? The smallest pop up. Okay? And you update its weight, its cost, and then it goes to all the rest, right? It goes to all the rest, and you get the smallest so far, and to keep going, but every single time you are going to put a lot, but at most it's O(n) squared, right? I think at most O(n) squared. So I think that won't work. I think that one will work. Let's try this. We have very little time left, so I don't want to do too long. So let's just give this a shot. If it doesn't work, we will debug this tomorrow. But at the moment, let's try. Okay, so it's gonna be Dijkstra, but we have to know the nodes. Okay, the nodes will be, we have a start, we have a target. These are the two nodes, and then for x1, y1, x2, y2, and cost. Ooh. How do you know from this? All right, so we also need, so we have the nodes, okay, and then we need to know the special cost. Costs. Special costs. Okay, special costs. Yeah, special edges. It's gonna be a dictionary. Let's call it default dict. I'll do a default dict. Okay, so we do a default dict of int, and in special roles, then we say if abs x1 minus x2 plus abs y1 minus y2. If that is larger than cost. If it's smaller than, there's no point putting into the nodes, right? That's basically the idea. So if it's larger than the cost, which means the cost is good, then we say nodes.append. So we'll do these two nodes, x1, x2, x1, y1. Oh, we need to tuple them. We need to tuple these. Just to make sure, right? We tuple these, then we'll append this nodes.append x2, y2, and the special edges x, y, y1.append x2, y2, and a cost. Okay, so we go through all this. We get a special, we get the nodes, right? Then what? Now, then we need to have the edges, the total cost, right? Total cost is going to be default dict lambda mass.inf. Okay, then we need a queue. And the cost, and say total cost tuple start is equal to 0. Duh. And Q is gonna be start. That's the priority queue, right? So we need to put the cost first, and the start 0 and the start 1. Okay, then we need heap queue, while queue. All right, so the current cost and ij equal to heap queue.heap pop queue. Right? So we pop it out. Then, ooh, that is not right. This should be a set. This should add. No, this is append. This is right. This is add. Ooh, add. because I want to go through everybody, right? But special edges. No, you go through every single one. You go through everyone, okay? You go through everyone, and if it's possible, so special edge, this is an special edge. Special edge x2 y2 equals minimum, whatever this is, cost. So now we store this. Aha, it makes sense now. Okay, so now what? We have ij, right? And we want to go through all the nodes. We go through all the nodes. Well, of course, we can say if ij I equal to maybe we do it I equal to target 0 and j equal to target 1, then we found it, right? Then we can just return the current cost. If not, okay, if not, then we need to go through all the nodes, right? Everybody. So we can say for next I next j in nodes, right? Then we can say next cost shall equal to current cost plus minimum of abs I minus ni plus abs j minus nj, right? Maybe we don't even do that. That's fine. So minimum of this is just directly go there. And special edges. And now we're going to yj to ninj. Right, we have a cost. So we get the minimum of these two. So this is the n cost, right? The next cost. And now we say if next cost is smaller than total cost of reaching ni and j, then total cost ni and j equals next cost, and heap q dot heap push q next cost ni and j. And of course this is actually, we should say while q and q0 q00 is the cost. If it's not equal to the total cost of q01, q02, then this means it's a wrong, right? So I say heap q dot heap pop it until it's equal. So if it's, I just say larger than. No, it should be not equal, because these two need to track each other. So if it's not equal, then we pop. All right, if it's equal, then we do this. And yeah, that's it. All right, this one actually I'm not sure. Let's try it. 1 1 4 5 and this. Okay. These two passes, I just submit it. Oh, we pass, so it is. Dijkstra. We pick out the special roads. We pick out special roads that result in cost saving and put the start and end of those roads into a list of potential node to travel through. Then we Dijkstra the list of nodes from start to target. Right? At each node, we try all the others. Since there are at most 400 nodes, this O(n squared log(n) solution will work. Try all the others until we hit the target for the first time. All right, so what are the smart people say? From the start to special roads. Yeah, you can do that. Yeah, I think it's the same idea. Edges. Visited. Yeah, that's alright. I mean, we got this. Priority queue and DP. Not DP. There's a DP in it. I think it's the same. So I'll let it pass. Yeah, this is just very basic Dijkstra. I don't see any other thing in this. Yeah, okay. So yeah, we're done. We're done for the day. I will see you guys tomorrow. Adios.